In this video, we're going to use our second case for when we are dealing with products of sine and cosine raised to powers. So if we have an integral in this form, sine to some m power times cosine to some nth power, m and m have to be positive integer values. Okay, so in case 2, we're dealing with when the power on cosine is odd. The video before this, we did an example where the power on sine was odd. Okay, so when we are dealing with case 2, what is our strategy? And what we want to do is we want to write n as 2k plus 1. All right, and then we're going to use the fact that cosine squared x is 1 minus sine squared x. That would mean that this cosine to the nth power of x could now be written as cosine to some 2k plus 1 power of x, which could be separated, and that would be cosine squared x to the kth power times cosine to the first power of x. And of course, we don't need to write this first power here. So we've got 2 times k plus that 1 value. And so when we perform our substitution, we know that cosine squared x is 1 minus sine squared x, so that would be squared, times this cosine x. So if I take that and I sub what I've just written here, this guy in for cosine, everything will now be in terms of sine, but I'll have this little leftover cosine here. And what we do in that case is we combine the cosine x with the dx. And so we can say that cosine x dx is going to equal the derivative of sine. And the reason we can do that, I didn't explain this in the first video, but if you think about d dx of sine x, well, d dx of sine x is cosine x. And treating this as a differential, that divide by dx, I can leave the d and multiply the dx up here. Okay, so cosine dx is d sine. That is why it's equal. So let's do an example where you can see this in action. In this example, we want to integrate cosine to the 5th power. All right, cosine of x to the 5th power, which is odd. You'll notice we do not have a sign here. That's okay. The problem will still work out. We can think about that as times sine to the 0th power. So to the 5th power, 5, if we want to write that as 2k plus 1, that's going to be 5 equals 2 times 2 plus 1. So we're dealing with the integral of the cosine of 2 times 2 plus 1 of x dx. So separating that, now I have cosine squared x squared times cosine x dx. So we said when we have that cosine squared, we're going to sub in our Pythagorean identity. And cosine squared is 1 minus sine squared x. That would be quantity squared. And then we're left with cosine x dx. So remember, d dx of sine x is equal to cosine x. Again, treating these differential terms like a variable, I can multiply that dx. So cosine x dx now equals d sine x. At this point, we would do our u substitution, and I'm going to say let u equal the sine of x. So this is going to be 1 minus u squared, quantity squared, du. And this, now it's very easy for me to write this as a polynomial, and if it looks like a polynomial, it's very easy to integrate using the power rule. So make sure you understand how I got to that step. Go back and look at the rule. This is just a strategy. This does not mean it is the only method that you have to use when you see these powers of sines and cosines multiplied together. All right, so if I move along with my problem here, this is the integral of 1 minus 2u squared plus u to the fourth du, which gives me u minus 2u cubed over 3 plus u to the fifth over 5 plus c. So we're done integrating. Remember, u was equal to sine x, so this is the sine of x minus 2/3 sine cubed of x plus 1/5 sine to the fifth of x plus c. So that is a method of attack when you have a product of sine and cosine. They're each raised to positive integer powers, and the power on cosine is odd. Okay, in the video before this, our strategy was when the power on sine was odd. We're going to do a third video in this series where neither sine or cosine have odd powers, when those powers are both even values. So we have a third strategy, or case 3. And what that deals with is when this power on sine and on cosine, those are both even. Okay, so this was the second video in the series, case 2.